Hi, welcome. I'm Alejandro Contreras, and today I'm going to present thermal fatigue of solder interconnects. So first of all, we need to know some background information. So basically, the use of electronic devices has become essential to our lives, and when these devices start to work, one of the most important parts is the temperature management of the system. So basically, the electronic package of this device starts warming up, which causes things such as the circuit board to be impacted by the temperature. So for example, the coefficient of thermal expansion of a glass epoxy laminate called a printed circuit board is 12 to 15 times 10 to the minus 6 centigrades. So at the same time, we can see the silicon IC located inside an electronic package has a CTE equal to 2.5 times 10 to the minus 6 centigrades. So basically, we can see here in the shape we have the silicon IC and the printed circuit board, and we see that they are connected by the solder joints interconnects. So basically, the solder interconnects generate an electrical connection between these two things, and they usually have a low melting point. But considering that the electronic devices are in constant use daily and they are exposed to constructions and expansions, basically this type of fatigue will eventually lead to the increase in fatigue life of the electronic device and may lead to some problems as it has constantly been used. So first of all, in the process, we see a table of data that they gave us. So we see that solder joint strain and the fatigue cycles. And here in the scatter plot, we can see how basically we can say that as the solder joint is smaller, there are more fatigue cycles. So this is logical as if the strain in the solder joints is much smaller, then the device can be able to do more fatigue cycles, meaning that it can last a much longer time than if the strain was much bigger. And we can see that the shape of the graph is kind of a logarithmic function or an exponential function. So second of all, now we change the values of the solder joint strain and we change it with the natural logarithms of these values, as we can see here. So basically we just do the same, we plot these values in a table and we plot them in the scatter diagram, and we can see how basically the graph has shifted left to a negative side, but basically the shape still remains the same. Now in point 3, we now need to change the values for the fatigue cycles using their natural logarithms and plot them using a scatter diagram. So here we see how they are changed to their natural logarithms, and here we see the graph. So here in the graph we see how it's basically a linear shape, and that's part of point 4, in which it says find the line of best fit. So we basically just get a linear regression out of this plot, and we basically have this equation right here. Now in point 5 they tell us that with this equation we basically change the values of the slope and the y-intercept into the new equation, which we can see here. This will be the final product. And in point 6 and 7 we basically need to solve for different things. So for example, a solder joint strain of 0.02 or fatigue life cycles of 3000. So basically here we have the final results of our values, and basically a conclusion to this project would be like, first of all, considering that electronic use is quite important, we can see how fatigue life is basically represented by an exponential function. But we can also say that in the process of analyzing this exponential function, we basically linearized this type of function in order to be analyzed in a much easier way than in comparison to an exponential function. And well, basically we can conclude that as the strain is lower, basically there is more fatigue cycles to the device.